Good morning, everyone. Well, it's great to see such a packed agenda for an exciting topic we've got here today. Just a couple of points. If you are, all these sessions are recorded, so you will be able to play back here and listen to these sessions again. And if you are at CPD, there is a touch point at the back where you can obtain some points for attending these sessions. So this morning, this session, we have got Nick Tune, who is the CEO and co-founder of Optimize AI. He's also a commissioner for the National Infrastructure Commission for Wales. And Nick's here to talk to us today about utilising digital twins in GenAI for the reduction of energy and carbon emissions in buildings. And I don't know about all of you, but it looks like you are also wanting to understand how this can be done. So, Nick, over to you.
Hello. Is this working? It's not working, is it? Hello. Is that okay? Yeah, brilliant. So thank you all for coming and welcome. As it was just mentioned, I'm Nick Tune, and I established Co-Builder only about 6-7 months ago with my co-founder Yassine Rezgi, and we're a spin-out from Cardiff University. And really, what we're trying to do is to utilize digital twins and generative AI to minimize energy and carbon emissions in buildings. Now, we might have heard or seen lots about digital twins and think, well, what value are they actually giving us? We might have heard and seen lots about generative AI and see, again, what benefit is there to the built environment? Well, hopefully, I'll show you a bit about how we can use the both of them to improve the built environment, and that is to reduce energy and carbon emissions within buildings. So Optimize AI, as I say, founded about 6 months ago. And as I'll talk about, it's the utilization of those two things, generative AI and digital twins to reduce carbon and energy in buildings. So start with the problem that we're looking to address. The problem for buildings is data. It always is in everything we do. It's a lack of data, and importantly, it's a lack of quality data. So if we're going to manage our buildings and reduce energy and reduce carbon emissions, do we have the data we need to be able to do it? The simple answer is, in most cases, no, we don't. So we're trying to fill in the missing gaps of that data to allow us to get actionable insights to understand how a building's performing in order to reduce its energy and reduce its carbon emissions. And as I mentioned there, 90% of non-domestic buildings don't even have a building management system. And of those that do have a building management system, I don't know if any of you have ever worked with them, I've never been able to understand them, so they're virtually ineligible, can't get any use out of them whatsoever. So we're dealing with a lack of data, and we're dealing with, when we get the data, can we understand it? So what's the solution? Well, our solution is to try to get some actionable insights via modeling with the use of generative AI, and I'll explain how in a bit. So, as I mentioned, where do we start today? When I go and speak to people about their buildings, I say, what information do you have? And the thing I always get back is, well, we've got a meter. Now, sometimes we have a smart meter, which is great, and I'll talk a bit more about that in a moment, of why a smart meter is helpful. We've got floor plans, and we've got some operation and maintenance manuals, sometimes. So often we're starting from that position of a very low level of information. But as I mentioned, smart meters are really helpful because they give us, at least at a building level now, access to data on a half-hourly and hourly basis, which we can actually use and make some sense of. What I should have said earlier is the focus of today's talk and the focus of the business is really on the non-domestic sector. Now, we can utilize a lot of what we're talking about in the domestic sector, but that's not the focus of our business. Our business is focused on non-domestic. So this is what we end up with. And the situation nearly everyone I speak to finds themselves in is this. How much energy do you use? How much is it costing you? How much carbon? And people generally don't know because they don't have the information. So what's the vision? When I speak to people, the vision that they have is to be able to manage their energy and carbon holistically across a whole site, from an individual asset level, down to the room level, to the whole site level, and to be able to deliver savings in energy, in carbon emissions, and obviously in pounds and pence. And to be able to do that for the buildings where they don't have a building management system, but also to get extra value when they do have a building management system, to be able to virtualize the data from the BMS, maybe supplement it with extra other data, and to understand how they can run and manage their building more effectively with the occupants. And to use that as a route towards a net zero route. So that's what I hear from when I'm speaking to big asset owners, of which I'll talk about a few more in a bit. So how do we do it? Well, as you can see, it's rather difficult when all you've got is a meter reading, some floor plans, and an O&M manual to get towards a digital twin that can give you some really good insights into how to improve. So I'll talk a bit more as we go along about how we do that, or how we look to do that now. So at an individual building level, and this could be a building with that has a building management system, what we do is we take the data from the building management system, various different ways of taking a BMS data, either directly via an API call or a data dump. There's lots of different ways. If it has a building information model, we could take the BIM model, or if it doesn't have a BIM model, to make a digital twin, we make a very, what I call a minimum viable BIM, in terms of the minimum viable information we need around zones and rooms, etc. And that, if you like, is to create the digital twin. Then we add the information about how the people use their buildings. Then we take our own data sets, and then we take massive data sets. So out there's, for instance, energy performance certificates for their rights and wrongs. There's millions of the data around how other buildings are performing from energy performance certificates. There's databases out there around how many thousands of other buildings are performing across the globe. So we take them, and then we utilize our models to understand the building and how it can perform. So what we're doing is we're taking, in this case, a building. It has a building management system. It might have some 2D plans. And we're turning it into, we're making a 3D model, and we're basically supplementing the data that they already have through the BMS with massive data sets, and utilizing the BIM to make a digital twin. Hopefully that explains. And the way that we do that is that the asset manager provides us with that information, and we create that in the cloud. For a group of buildings, or buildings where there's no BMS, there might just only be a smart meter. It's really difficult when you haven't even got a smart meter, I would say. But where we have a smart meter, we can take the readings from the smart meter data. We can take how the people are using the building. And then we can also take those massive building data sets. And just by some basic information, we can make a really rudimentary model of the building, a really basic model of the building. And we can fuse it with the data sets to start giving some understanding and some insights. And the kind of things we'd be showing is how the building should be performing as an average, because we know how it should be from energy performance certificate type data and massive other data sets. We're connecting in the data from the smart meter so we can actually know how it's performing now. And then we can see the difference between the two, and through the model as well, then to start understanding how the building's performing, how it should be performing, and what it would look like in the future in terms of prediction. That's, if you like, at the most basic level when there's very little information. And I'll show some examples in a bit. So, getting slightly technical now. I was asked to kind of talk a bit kind of how we actually do this, not just, if you like, the fancy pictures, which I'll come to later, but how we do it, I'll try and explain now in more detail. So if we start with a limited data, We'd create an energy model, as I talked about, an energy simulation model, either directly from a BIM or from the information we have, the basic information that people give us. That could include the O&M information, could include floor plans, could include some basic information about the building. So that's just a model. Then we've got some limited data sets coming to us. We might have that limited data from a smart meter. And that's when we do the data enrichment of the model, and we utilize our algorithms using the massive building performance data sets to do generative AI and something called transfer learning. So we're collecting data from sensors, we're supplementing it with the building model to get some knowledge. Then as we go up the value chain, where we get more data, so for instance, we might have a building management system, or we might put extra sensors into a building, allows us to make something called meta-heuristic models. We're getting in much more detailed information on how the building is performing. And that allows us to develop optimization models and optimization scenarios. Remember that what we're doing is we're always using a simulation model coupled with an artificial intelligence general AI model based on how the building is performing from its own data, from the meter reading, the BMS, the sensors data, and those massive other similar data sets. So we're fusing them together to get us the maximum insight we can get. And then we create that digital twin. So the type of inputs that we looked for clients to give us are some really basic information at the entry level. The type of the building, the age of the building, the area size, the location, what type of HVAC system, what type of renewable energy systems it has, adding the meter data, as I mentioned. And then we are running that through the algorithms, through the model inputs, through the area inputs we have, and then we have the output that shows the energy consumption, how it's predicted to perform. And then we have the client outputs. So that, if you like, the bit in the middle is the intellectual property, if you like, of how we create the understanding from all that information. And the type of information, to go even deeper into it, to, I guess, help you understand a bit more, is things like the building data itself. So, in other words, the size of the building, the number of floors, the number of rooms, the type of information we can glean from a model, such as a BIM model, or from information people give us. We take GIS type data, so location type data. We take Google Earth type information, map information, and then down to the data such as things like, as I talked about before, an energy performance certificate, and then individual specific data from sensors and from meter readings. So it's a combination of all that together, and that then goes through the semantic middleware that creates the digital twin and does the optimization. So the type of output that we're building, as you can see here, will then, from all that information, basically see how the building is performing against how it should be performing, and predict how it will perform into the future, and then also develop optimization scenarios of how to reduce the energy and carbon. And we're doing that by we've basically put in scenarios that how the building should be running, but we allow the customers to be able to adapt those scenarios. And it could be basic things such as airflow rates, it could be air quality rates, it could be temperature, it could be lighting levels. So you can put the parameters that the machine, in effect, is working towards to put you down to. So it will then tell us things such as, we think that we can see that this building isn't operating against how it should be, against the norm. We believe the reasons are these specific reasons, and we believe in this certain type of scenario, such as HVAC system, we believe it's operating inefficiently, and therefore, by making this change, we can derive a 20% saving or a 40% saving, or whatever it may be. And we can then estimate how much energy they're saving, how much carbon they're saving, how many pounds they're saving, and then how to achieve it. And the next level of development we're doing is we're not only telling them where the savings are coming from, or where the savings can be made, but then telling them how to create those savings. And that then is basically through like a large language model that is finding direct guidance around how to specifically make that improvement and enact that improvement, and even linking right through to getting the tradesperson or the manufacturing product that you need to actually go and install it and make that change. And then the added bit on top of that is actuation. So either directly through the building management system or putting your own actuation, the machine can then run the building. Best analogy is as a car, a Tesla. You know, we're getting used to the fact now that we have the human driving the car partly with the machine. It very much works like that in many Teslas and even the Hyundai car I have. Well, that's the route we're going to the building. The one thing I talked about up till now was about telling the facilities manager, the asset owner, how to improve. The point that we get to then is actually the actuation where the AI is actually controlling it. Now, I think there'll be a mixture, exactly the same as there are in cars at this moment, where people don't fully trust an autonomous car. But if you've driven a Tesla or an electric car recently, that you'll find there's a huge amount of the machine actually helping you in that delivery. So what we're going to find is that kind of quasi-human and AI in terms of the operation of the buildings. And the machine allows us to do that. Then we can break it down and look in more detail. And then what we're seeing is the actual energy performance, and that data comes from the smart meter or the building management system, the predicted or estimated consumption that there's going to be going forward, and we can look backwards, and then, if you like, the optimized. And the optimized scenario is based on your parameters, because as we all know, the easiest way to save energy in a building is just turn everything off and tell everyone to leave. But we can't do that, so we have to have minimum parameters in there. We can even have something like, you know, again, picking a car. In my car, I've got sport mode, normal mode, and eco mode. We could even have the building run at eco mode, where it's just running down to the minimum of the requirement. So the minimum of the temperature, the minimum of the air ventilation, the minimum, whatever the user wants to set it at, will then show you how the type of saving you can achieve by that. Now, this is a digital twin that we're looking at now, because what we're doing is we're running scenarios and we're seeing it in a virtual environment based off data that's coming from the real physical asset, i.e. the data from the smart meter, the data from the BMS. We're running simulations, we're running predictions, and we're running optimization scenarios to allow the user, the owner, to optimize it effectively. As I said, they can either do that manually, or they can do it via actuation, or they can do a combination of both. And this here is just showing, for instance, then breaking it down to an individual room level, and then a component level, and looking at an individual sensor. So we can, if you like, look across from a whole estate wide, so many hundreds of buildings, to an individual building, to an individual room, to an individual component. It all relies on data. But the really important point, if there's very limited data, such as just a smart meter, just an O&M manual, just some information about the building, we can still give some insights. Not so much granular here at a room level. They would be probably at a building level, but even then we can see how the building should be performing, how the building is performing, and deduce from the many other thousands of data points we have from thousands of other buildings, what are the specific issues we believe are happening and how to improve it. So it's about giving insights where there currently are none, as well as working all the way up to the full BMS within a building and getting to the point of actuation. So that's in effect what we're doing. We're doing it at the moment with the technology we developed it in Cardiff University over several years. We've got patents about how to do it. And now we're working with, if you like, friendly customers in testing it. We're going from technology readiness level 7. So we're working with the Catapult, the Connected Places Catapult on Bristol Temple Meads train station, working with Network Rail on Reading train station. We're working with Cranfield University on their aerodrome. We're working on some offices. So we've got lots of different building typologies with clients that we're testing this, if you like, and working with this at the moment. So why now? Well, I was asked this question a lot when looking for funding last year, because I spent the whole of last year writing the business plan, getting funding, and asked this a million times. Well, first, we're in a climate emergency, obviously, and we need to do something now. Businesses are going bust every day because they can't afford their energy bills. We've got to make massive savings in carbon. You know, we need to reduce our carbon emissions by 50% to achieve the 1.5 to 2 degree global warming, which is just by 2030, which is 6 years. So if we're going to be 1.5%, we've got to cut our emissions by half. So that's massive. We need to save money. It's pretty obvious. But I think the big reason why now is we didn't have the computing power before. So we had the lack of data, obviously, the lack of information, obviously, but AI, ML, and computing power has opened up an opportunity that never existed until literally, I'd say, 2 years ago. So it's only now that we can actually start getting these insights and running these types of models to be able to understand these buildings. So it's very much, I would think, of the time. Technology now is finally allowing us to do it, and we need desperately to do it for the obvious reasons. And I guess the whole BIM mandate and this event here today around digitizing buildings is really helping, because at least sometimes when I speak to people, they have a BIM and it might be half decent that we can actually use. So that helps makes it a bit easier. So as I mentioned, we're working with various big organizations, asset owners. We've done projects, test projects within the Cardiff University as we were developing it. And we're doing another project at Ebbw Vale, which is a big site which has got a leisure centre, it's got an old offices, it's got a college, it's got a school, and optimising that and looking at optimising their district heating network. And the first iteration we made a 20% saving and a massive amount of carbon reduction. We've done projects on leisure centres. I think we've all heard, you know, swimming pools, leisure centres are going bust because they can't afford to heat. And we've done previous projects where we found really significant savings. And these savings aren't by making massive capital expense. These are just by optimization of the controls. How you're managing your building, how you're doing your set points, how you're running your MVHR unit, what are you doing with your temperature, what are you doing with your air changes, that type of cheap saving, as well as obviously putting in LED lighting and all those other things. Those are some kind of examples that we've done previously. Hopefully this runs. And here's a few examples here that you'll see. So the top left is a citywide digital twin of Cardiff Bay, and that's just looking at the buildings in the Cardiff Bay area to see how they're performing against how they should be performing. Now, simply, that is just a case of taking the smart meter data and having targets around how those buildings are performing, and then color coding them up red, amber, green to see how they're performing against their target. So for the asset owner across an whole asset level to see how it's performing, to see how what's wrong, and then to start looking at it, how to improve it. The top right was in Qatar for the Qatar World Cup, and that's looking at an individual building. Here you can see a detailed building information model, and there we're looking at how do we optimize that building based on reducing carbon, but also around air quality, because they wanted a lot of air changes because of COVID-19. COVID-19 was still pretty big when the Qatar World Cup was on. So they were modelling how to keep air quality high whilst reducing carbon emissions or energy consumption within that building. The bottom right is Reading train station, one we've just been working on now with Network Rail, and there we're looking at when we did the audit, we could see that nearly all the energy came from lighting and came from lifts and escalators within the train station. So we put extra sensors in the station to see how the heavy machinery was actually working and when it was working. And then from that, we've optimized how to run the machinery to generate those savings within the station. And then finally, the bottom left is Milford Haven Port docks, and then that actually was looking at their fish processing, and there they had a PV farm, and they were looking at how do they make the most of all the PV they're generating within their massively energy consumptive site in terms of managing and freezing the fish, and then also when to trade it back to the grid, when to use it, but also how to optimize the chillers within the actual facility within the docks. So those are some examples of some of the projects that we've got going on. Now, before I finish, where's this all going? Oops, it's gone a bit funny. Hope you can see that. Where's this all going in the future? So, we've gone from cloud computing to the state of the art now, if you like, is a digital twin, where we've now got a 3D representation of an asset, and we've now got some data between the physical and the virtual. We're now moving into generative AI and transfer learning. So we're transfer learning from the big data sets. That's where we're operating at the moment. So we've got a digital twin, we've got the simulation, we've got a digital twin, we're coupling it with generative AI and transfer learning. Now then we're moving up the value chain around things like fast machine learning, edge computing, computing on the edge, which allows stuff to go even quicker, distributed ledger, blockchain, and then up to quantum computing. So the point is this data leap has allowed us to start getting insights into our assets where data is poor. I think if there's one thing I kind of want you to remember, it's we can now start getting insights where maybe we couldn't previously. But the speed of change, the growth of AI, is here. It's here to stay, and the opportunities it opens up to us will be massive, providing we can, if you like, jump on the tails of this and really make the most of it. So hopefully that's kind of given you a good insight into the art of the possible with taking the data, the information you have at a building level and actually getting some extra insights that you currently wouldn't have, and as well as where you've got some good insights, getting extra benefits, so extra energy saving, extra carbon emission savings, squeezing the extra out where it doesn't exist. So hopefully you can see the potential, the opportunity, what we're working on, and any questions, please feel free.
Hi.
Yeah.
Hey, great presentation, Nick. Thank you. Quick question about the human element. So a building is only as optimized as it is comfortable to work and exist in for a human. So I'm thinking about when we need to bring that feedback loop back in, how important it is to do it early. Taking VAR as an example in football, the tech might be great, but if people don't see it as useful or adding anything to their experience, it doesn't necessarily then get a very favorable reaction. So how do we bring the feedback loop in? How important is it to do it soon? And what happens if we don't?
So obviously the obvious answer is massive. I'm speaking to a university asset owner. They've reduced energy hugely, but then everyone's now complaining of the air quality in the lecture theatres because it's terrible. So we have to look then at the difference between that and the ventilation and managing carbon dioxide emissions, for instance, around air quality. So how the human wants to use an asset is vitally important. Again, I don't know, I do like the kind of Tesla kind of car analogy. I have an eco mode in mind. Press eco mode is awful to drive, but it's saving me loads of energy. We can do the same in buildings, but we don't necessarily keep our people happy. So it's definitely a payoff between how do we keep people as comfortable as possible whilst minimizing the amount of energy and carbon emissions as possible. And it's never, the answer's never 100% because, as I say, we just throw everyone out. So, but getting their feedback is really difficult and massively important in the building of all of this. Thank you. Good question.
Well there, Nick.
Hi.
I think I just saw this hand here first. Yeah. Oh, we got somebody over here, Becky.
Hi there. Yep. Thanks.
Don't know where I'm looking.
Thanks very much for that. Really interesting. You mentioned at the start that BMS is often somewhat inadequate or very hard to interpret the data. To what extent do you see the classic building automation companies responding to this, or do you think it's fundamentally too hard for people to kind of adapt to the BMS, or do you see there being perhaps a bit of both, this type of solution plus that?
Yeah. So the question, if I heard it right, was about how do the BMS companies type respond to this. What I'd say is we've worked with most of them, so we've worked a lot with Schneider, and they are doing a lot of really good stuff. So it's not as if all the BMS companies are, no good and they can only give rubbish data. That's not the case. Most of the old BMS systems are no good and do give rubbish data. That is the case. But the BMS companies are developing some nice technology to help give you some really good insights. The only thing I would say with it is it's pretty expensive, in fact, very expensive to install. So I guess if I was them, be slightly worried about the whole virtualization of the BMS, about making it, the use of IoT, LoRaWAN, etc., makes it easier to get the data. So I guess, if I was working for them, I'd be slightly concerned about that. But that's not to say that there aren't great solutions from Schneider and Honeywell or whatever. There are, but they're just few and far between and pretty expensive.
So how much data you need?
Yeah, it's okay.
Just need to speak up.
Oh, hi. How much data do you need to generate digital twin to make a good prediction of future?
So in terms of what information you need, again, you can start with really basic one, which we just get information around how the building's constructed, the age of the building, and we take information from GIS type data, and then the whole point is by using the big data sets, we can start getting some insights. Now those insights are not going to be hugely specific or granular, but the whole thing we're trying to do is to give some insights where there currently are none. So at the moment, if you don't look at your meter reading, you don't do anything. If you've got something that's showing you how your building's performing against how it maybe we think it's going to perform, actually might get you to start thinking about making a difference. And we can then start giving tailored guidance of how to enact the change. So that would be at a building level, and to get you as an entry point, thinking about it and thinking about improving from very little information. But right the way through, if you've got a really good BMS and loads of sensor data, then we can have a really detailed digital twin and give really good insights and make it much more granular and get much higher amount of savings out of it. So the point is it's a whole spectrum, but the important point is we can now start giving insights where there's very little information, where at the moment there are no insights.
Hiya, my name's Izzy Webb. I'm from DB3 Group. You mentioned that you have an LLM providing advice, and I'm wondering what measures you have in place to check if the model's hallucinating, when obviously accuracy is very key for building owners.
Yes, good question. So something I've told our guys in the development is that we're going to show accuracy the whole way through, to show what the percent of accuracy is working to. Which is relatively easy to do, so that you can give the building owner the confidence in so we're not saying it's 100%, it's about guidance, isn't it, in terms of the realms of what you're working. So that will obviously vary, depends on what you're doing. Then in terms of, if you like, we're only using the LLM, the large language model, sorry for those who don't know, think ChatGPT. We're only using that for guidance type information, as in mining information around. So for instance, say you have a problem with the HVAC system and it's in school, what's tailored specific advice for that, how to improve the HVAC system in that school. That's the only time we'd use the LLM. We're not using the LLM in the models that we're using to understand the building and to operate the building. They're totally different AI models.
Any other questions? So I've just got one down here, just on your right. Thanks.
Hi, thank you. My question is regarding the output. Although you mentioned that it's still work in progress towards advice giving, more like advising the client on how to make those improvements. But I'm quite curious. In your presentation, in the output session, I saw the place where it mentioned something like installing double glazing window, something, and then view scenario. What kind of the interface when you want to view those scenarios, what does it bring out? Is it text-based, or is it something that, for instance, if you have clients, maybe local authority, people who don't have those kind of skill sets to understand this, how is the interface going to look like?
So our plan wasn't to build a tool that tells you what physical upgrades to make in a building. To be honest with you, you could run IES who are over there, and you could work it out yourself. But as an endpoint, it can do that as well. In terms of, we can say, well, this insulation will give you this improvement. We can easily put that into the model and show you how that's working, and then you can go to specific advice of how to purchase that and use it and whatever else. And that's where the LLM type comes in. What's really important, though, is actually, because most of what we're really targeting is around the controls around how you run your building, as well as you could have advice around the physical element. But interesting, if you did put a load of insulation in the building, you would probably need to change things such as your set point of your heating system, which people don't often think about. So it's actually, there's a whole control element as well as the physical element. So we can do both, but the main target of what we're looking at is about the control element of the asset.
Thank you for the talk. One of the questions I have is, how big is the benefit of continuously monitoring a building versus kind of just doing a, let's say, one-off calibration and iteration and basically setting up the configurations in the desired mode?
So the question was, what's the benefit of keeping it live? Well, the main thing with keeping it live is you've got machine learning, so you're learning how the building's performing. And no building ever acts like a one-off in one moment because of us humans mess it up. So actually, by continuously monitoring, we can then understand how the building occupants are using the building and get much better granular advice on how to actually control the building, predict how it's going to perform, and develop optimization strategies going forward. So a one-off snapshot, that's the way we've always worked. We're doing energy audit, and that's a one-off thing. And that's okay at that moment in time in that specific use case. But we need something that's live, that actually learns, and that can actually then predict ahead and optimize ahead.
We've still got time for a couple more questions. If Nick can keep going, he's been firing and answering quite a lot there. So has anybody else got another question for Nick? Yep.
Thanks for that, Nick. It's really informative. I was just wondering around, you mentioned the Qatari example, and that being driven by air quality as opposed to necessarily CO2. And we've obviously got new buildings being designed to well standards, and I was wondering whether you can apply different well standard thresholds to your AI learning to deliver the accredited design.
I guess the simple answer would be yes, because that's a scenario. The scenario is around the well standard, around, I don't know it well enough, I know a little bit about it, but if it's around certain air quality, that's just a scenario metric you're putting in. And then what you've got is the trade-off between that air quality and the management of the asset to your other scenarios, which might be around saving energy or saving carbon. And what you're trying to do is come up with the most optimal, that's what the machine learning's doing, the most optimal way to make the biggest amount of energy saving and the biggest amount of carbon, whilst providing that, for instance, other point which could be about air quality. So that it's just another data point and another scenario that goes into the model.
Anybody else got something they want to add? It's quite an interesting, a very interesting, controversial topic. So AI, we've had quite a few good questions there. So if there's nothing else to add, then I'd like to say thank you very much, Nick, for your fantastic presentation.
Thank you all.